So now we are going to do the force in uniform circular motion for a banked road. Okay, by banking we hello students. So now we are going to do force in uniform circular motion for a banked road. In this case, basically there is a car which is moving along this road, right, in this circular motion, and we have seen that this road is banked in the upward direction somewhat like this. So if I draw like this, the road is inclined like a plane like this, and the car is moving over this inclined plane in circular motion. Okay, so let's see the dynamics of this. Now if I draw a free body diagram again, once again, for this case, it's going to be something like this. Basically, this is the banked road, right? There is some inclination theta and the car is moving along this road, alright? So it's moving like this in a circle somewhat like this. If I draw the forces, that's going to be like this. This is going to be mg, that is the mass of the car, and this is going to be the normal reaction, right, in the upward direction. Okay. Now another important thing is, okay, one mistake have been done here. You can clearly see this normal reaction is going to be along the surface, right? Basically perpendicular from the surface. So normal reaction is going to be like this, okay, and not in a straight line. Now here, if the normal reaction is this and this is the mg, I'm going to take the case in which there is no friction as of now. Okay, so this is a particular case or an ideal case in which there is no friction between the car and the road. Okay, so in such a situation, you can clearly see that the force which is responsible for the centripetal acceleration is basically this horizontal component of the normal reaction of the car. Okay, so here if I draw this axis, x and y axis, you can clearly see it's going to be like this. Okay, so let's see the angle which is going to get made here. This is theta, so that means this is going to be also theta, right? So this means basically this line and this line, this is 90 degrees, right? This one is 90 degree and this is theta, right? So this means this is going to be 90 minus theta. As a result, this will be theta. Okay, so let me just erase the other parts. So there you have basically theta, and then theta is over there. So this means according to this, this is going to be n cos of theta, and over here along the x-axis, horizontal x-axis, that's going to be n sin theta. Okay, now here you can clearly see that in the upward direction, this is the n cos theta which is balancing with mg, right? And these two forces are equal to each other because there is no motion of the car along the y-axis. Okay, it's moving along the x-axis and the resultant force is in the left hand side direction. So that means n sin theta is equal to the centripetal force. Okay, let's just write that. Fc, that is centripetal force, that is equal to n sin theta. Another important thing is n cos theta is equal to mg. Okay, n cos theta is equal to mg. Okay, so or let me write this in this way. Mg is equal to n cos theta. Okay, now if I say that this is equation 1 and this is equation 2, let me just divide the two equation, right? Let me just divide equation 2 with equation 1. So that means Fc, that what is Fc? Fc is mv square upon r, okay, divided by mg. Okay, this is going to be equal to n sin theta, right, divided by n cos theta. Okay, you can clearly see here n and n is going to get cancelled and sin theta cos theta is going to be equal to tan theta, right? In this case, you can see that basically mv square upon r and then divided by mg, right? So this is going to be equal to mv square upon r divided by basically multiplied by here mg. Mg will come here. Okay, that means m and n is going to get cancelled and I will have this is equal to tan theta. Okay, so you can clearly see v square is going to be equal to rg tan theta. Rg tan theta, that means v is going to be equal to, right, under root of rg tan theta. This is the velocity of the car, the safe velocity for the car when it is going on a banked road and in a situation when there is no friction. So V is equal to rg tan theta. You can clearly see that in this case as well, it is independent of the mass of the car itself. And another important case is, this is the critical velocity once again. Okay. Now you can clearly see that the meaning of this is, if V is greater than under root of r g tan theta, okay, in such a situation what will happen, if V is greater than r g tan theta, okay, it will slip outwards because the velocity is very high, okay, so the car will start to slip outwards. Now as a result, what will happen, the radius has increased, okay, so that means it will slip a little bit outwards and the radius has increased. So as a result, then the velocity will adjust accordingly and the car can start moving with that particular velocity, okay. So it will slip outwards, and if V is less than this under root of r g tan theta, in that case the car is going to slip inwards, okay. As a result, the velocity is going to drop and eventually it will start to move at a different radius, okay. So it will slip inwards, and when this V is exactly equal to this, there is going to be no slip and the car will keep on moving with a perfect uniform circular motion, okay. So that's your uniform circular motion for a banked road for the case when there is no friction. After this, we are going to do the same thing with friction, okay. Thank you. So now we are going to do the same derivation, right, for a banked road on which a car is moving, and in this case there is friction, okay. So this is for the case in which there is friction between the road as well as the car's tires, okay. Now if there is friction, that means the tendency of slip in this case is going to be here in the downward direction, because I'm assuming that the car is moving with a greater amount of speed, okay, and it's moving with such a speed that it may slip outwards, okay. So it's moving with that speed. So that means that's going to be the maximum velocity of the car at which it may slip outwards. So there is going to be this limiting friction, right, in the downward direction, so that it's stopping the vehicle to move in the outward, basically out from the circle. All right. So we know that if F is along this surface, it's along the surface, right? This is theta. So that means this is going to be theta, right? Now, if this is theta, so as a result, this is going to be F cos theta, right? And along y-axis, there is going to be, once again, F sin theta, okay? Once again, in this case, this is just about to slip, right? So all the forces are balanced. Now, before we move ahead, we can basically do the same exercise. Here, I'm going to write all the balanced forces along x and y direction, okay? Along y direction, the forces are balanced. You can see this is going to be n cos theta, right? So along y direction, n cos theta is going to be, so here let me write all the equations, right, which are getting balanced with this, okay. Now in this case, along y-axis, I have n cos theta, which is going to be equal to mg plus f sin theta, right, mg plus f sin theta. All right. Now this is equal to this, and in this case, along x-axis, these forces are going to be equal to the centripetal force, which is going to provide the necessary acceleration for the object to rotate, okay, not rotate, go under uniform circular motion, okay. So I have n cos theta, actually n sin theta, which is equal to, and it gets added with f cos theta. Now these two forces in combination are equal to the centripetal force, which is equal to mv square upon r, okay. But we know that in this case, we understood that basically this is the limiting friction case in which the velocity is maximum. So for limiting friction, the friction is equal to mu times n, okay, or ideally basically friction is less than equal to mu n, but in the case of limiting friction, this is going to be equal to mu n. So let me just replace this part in this equation, and I will have this as n cos theta, right? Or let me just replace directly into this equation over here itself. right? This part and this part. Okay. So along the x-axis or basically y-axis, this is n cos theta and this was f sin theta, right? So f is going to be equal to mu n sin theta, and here this is going to be equal to mu n cos theta, mu n cos theta. Okay. Now I'm going to solve for n using equation 1. If I say this is equation 1, this is equation 2. So let's just derive for n what exactly is going to be this equation. So here n is going to be equal to, right? Let me just replace this like this, n cos theta, right, minus mu n sin theta. Okay, this is going to be equal to mg. Okay, let me take n common. So n, if it is taken common, this is going to be equal to mg divided by cos theta minus mu sin theta, right? Mu sin theta. Okay, so this is the value of n that we get. Okay, now if this is the value of n, shall I put this in equation 2? Okay, I'm going to put this value in equation 2 and let's see what happens. Okay, in equation 2, this is going to happen that here each and every value of n is going to get replaced with this part. Alright, so let us now put this equation in this equation number 2. So what exactly is going to happen here? In the place of n, this is going to be equal to mg upon cos of theta minus mu sin theta. Alright, multiplied by sin theta over here. Okay, so this is basically n sin theta plus mu times n. Now n value is mg upon cos theta minus mu sin theta, right? Okay, so mu n and then multiplied by cos theta. Okay, and now this is going to be equal to mv square upon r. So this is equal to mv square upon r. Okay, let me just erase this part. Okay, now over here we have to just simplify this equation and then derive for v, right? Almost all the different things we have is right over here. Okay, now in this case, if I divide this equation by cos theta, right? If I'm going to do that, so let's see what exactly happens here. So I have mg, right? Sin theta upon cos theta is going to be equal to, right? I'm going to divide the numerator and denominator by cos theta, right? So sin theta upon cos theta is going to be equal to tan theta divided by cos theta is going to be equal to 1, right? Cos theta divided by cos theta is 1 minus mu tan theta, right? Then this is going to be plus mu times, right? This is cos theta upon cos theta, so this will be equal to 1 itself in the numerator, and in the denominator this is going to be equal to mg divided by cos theta, it's going to be again tan theta. Okay, no, not tan theta, actually cos theta divided by cos theta is 1, right? Minus mu tan theta. Okay, and this is equal to mv square by r, right? This is mv square upon r over here. Okay, so this is the overall equation that I get. Now let me solve this for v square. Okay, so I'm going to erase this part, and here if I solve this for v square, okay, just rearrange the whole equation and let me write this for v square. Okay, now if you can clearly see this v square, this r is going to go over here. Okay, and this 1 upon 1 minus mu tan theta I will take common. Okay, so doing that I will have this as rg, okay, and rg mu s plus what should be in this case? In this case, this will be mu s plus tan theta. Okay, and this is going to get divided by rg mu s plus tan theta minus minus this is going to be equal to mu tan theta. Okay, so this is going to be the final equation that we have. Now let me just put it over under root. So v is going to be equal to rg mu s plus tan theta divided by 1 minus mu s tan theta. children, remember this is mu or mu s. Basically, eventually, this whole mu, that is the coefficient of friction, is coefficient of static friction. Okay, so it's your wish. You can write this as mu s, or you can simply write this as mu. The final equation is going to be eventually the same. Okay, so that's your maximum velocity for the car in the case when you have this. Okay, okay, I forgot to put g over here. This is rg mu s plus tan theta. Okay, so rg mu s plus tan theta divided by 1 minus mu s tan theta. You can clearly see from this equation you can get directly to the banked road, in which case basically there was friction and this is basically horizontal. So you can see when this inclination is horizontal, theta is going to be equal to 0. Put this 0 over here, this will be 0, this will be 0. Eventually you will have V is equal to under root of Rg mu. Okay, so this was the equation for the turning of a car over a level road. Okay, so in this case, this is basically satisfactory with that as well, and in this case as well. Okay, so that's your final equation for the maximum velocity of the car on a banked road in which there is force of friction. Thank you.